Hey guys, I hope you guys can hear me. I'm trying to use my iPhone, and it has a much better camera, and I have my desktop. So I'm hoping that this is going to be sufficient for us to be able to have this conversation. I won't take too much of your time, so we'll try to keep it like 30 minutes max, and then I'll take questions. I just want a few of you guys to just raise your hand if you can hear me. So I'll check on my desktop and see if you hear me. Just any one of you, if you just say yes, that's already enough for me to get started. Awesome. Great. Perfect. So I have Kaustubh, Sanjay, and I also have, so my LinkedIn. I see on my StreamYard, I use StreamYard as an app, which is now part of Hopin, to actually run these sessions. I haven't done it in the last few weeks. We've been super busy, but so essentially, I don't see myself, but I can see, for example, I see Rahul, hi, Arun, Sammy, Yogesh, wonderful. So I can hear you guys. Um, so this is the series of MLOps in which we'll talk about successful testing strategies. In our last session, we spoke about the whole conundrum, the whole, well, what is MLOps and how to take your AI or machine learning or deep learning models from their current research state all the way into production environments. And it's a huge and it's a wide topic. So I thought, let's try to break these chunks and try to understand these piece by piece. So that's the whole idea. So let's get started. So what are we waiting for? Um, so so basically last time, let me just kind of go to my slide here. Yes. So successful strategies, testing strategies is key for you to actually run your machine learning models, actually deploy, monitor, and eventually have a successful feedback loop to have your machine learning models in production. The key is, I see that I should be looking at the camera. By the way, NVIDIA has just, they have this awesome sort of eye correction technology, which they spoke about in GTC. So if I'm looking elsewhere, it just sort of, positions the eye. So the eye contact is made. And anyways, so the successful strategies for testing involves actually two things. The first is there has to be some kind of an understanding of what are the performance strategies that I need to have in order to be able to deploy these successfully into production. And the second is I'll talk briefly about testing strategies. What are these, and how does it work? So next slide. I hope the slide transition happens. Yes, I'm seeing that happen. So I guess you guys know me, so it's no big deal. Um, so shipping robust models into production, and this is what we're going to be talking about. So essentially, what we are trying to understand is whatever that happens in laboratory, in labs, in AI labs, and I'm sure there are a ton of AI labs all over the place, is never 100% guaranteed that you will take your models and have these succeeding in the real world. And for machine learning models, it's a similar story. Research, awesome, exciting, lots of experimental work going on, but when you put it into production, the world looks very different. So not only the production environment actually typically very different from the development environment, the commercial risks associated with your models in production are much higher. So here I've sketched a sort of a carve out of a diagram, and there's a much bigger picture that covers the whole ML ops ecosystem. So that's what you see. We'll sort of explore these a little bit. And I have tried to put focus on this aspect, which I put it on green, which is explainability, interpretability, reproducibility, and security aspects, and specifically also risk mitigation. Because unlike other technologies that we've been using in the past in any machine learning or deep learning model, ethics and data privacy aspects like How do I mitigate risks in terms of auditing, et cetera, from bias, fairness, et cetera, perspective needs to be addressed. And once you have done that, only then you can successfully deploy these models in production. Is my argument. So you see there, just kind of going through this sketch a little bit. You can have multiple models that you're feeding it into your runtime environment. So we'll talk about runtime environment a little bit. And then there's model risk registry and a bunch of other aspects. Quality assurance is a very important aspect of your releasing your application into production. So QA definitely has his own individual place inside your release management regime within your IT. And then on the right side, you see here, so there's performance testing and documentation, and eventually your testing and monitoring. So you feed your models into runtime environment, and then you test your models. And eventually you make them production ready, and only then the model is ready to be deployed. So that's this whole sort of thing in MLOps. And the commercial risks associated with the models in production are way too large, much greater. It's not a joke. It's not Kegel exercise. It has to be a very, very managed extremely well. So this is the purpose, and that's why I illustrated this diagram. So getting your models ready for production. So let's take a look how it looks, how it should look like. So I just say, well, sort of model development is great. It's fun for cowboys, but when you go into production, you need some really experienced players who have been doing this kind of a rodeo writing for a long time. So let's take a look at the runtime environments. What are the key aspects and key considerations of a runtime environment? So in a production environment, you have a wide variety of forms actually in production environment. As some of you obviously may be knowing, if you work on a day and night inside your data center, working in your development, testing, acceptance, and production. Productionizing your computing workloads, whether AI or any other workload. So custom built services, you have your data science platforms, all kinds of services like TensorFlow serving, PyTorch, Lightning, and all the other new models that you have in place, and even sort of low-level architectures, infrastructures like Kubernetes, K8 clusters, etc. And maybe you also use some kind of embedded systems. It could be JVM or some other system. So it makes a lot of sense to actually pay attention to how you're going to take these systems and deploy into production. So ideally, models actually running in your development environment should be validated and sent as is to production. Meaning there's no intervention. You're not making any changes on the way. You're not ruining your own the release management regime. Unfortunately, the ideal scenario does not always happen, and we deal with it on a daily basis. It's challenging. So there's never a project that has been prepared in development and has landed successfully in production. If there is, then I think it must be a wonderful job. So basically, runtime environment is one aspect that we're going to take a look at it. So there'll be 4 considerations we'll be looking at. So how to sort of take development to production move, and how to sort of, what are the things that we need to do in order to take our machine learning model from development to production. There's tooling optimization, what kind of a tooling, how should I go about it? Then there's performance considerations, and then you have your data access considerations. How am I going to sort of access data? What are the aspects that I need to sort of consider when I do that? So let's take a look at the development to production. So here again, I've said my deployment strategy is in place. I know what I have to do on the right, and I've just taken an example. So there are 2 kind of ways of going forward. You could have a homogeneous and sort of a seamless environment where you work with one vendor. You don't have much struggles in terms of all kinds of interoperability and portability, et cetera, issues. And for example, I mean, I just sketched this diagram, and this is the representation, let's say, of a homogeneous environment on your right, on your left. And let's say you're using Microsoft Azure as an example. It could also be Google or Amazon environment. So you have the methodologies and the skill sets, et cetera, required are pretty much in place, and you know what you should be doing. And let's say that you plug in into the framework or an MLOps framework of a company like Databricks, for example, that has probably the most advanced ecosystem out there. There are other companies that are also emerging. So, just giving an example, just illustration. Um, so that is one side of the spectrum. So basically, you're reducing the number of clicks. Essentially, that's what you want. Release management should have a limited number of clicks, meaning limited number of risks, limited number of making mistakes as you ship your models to production. And pushing to production reduces, so there are lesser commands, and you can actually ship models. You can do a lot of interesting things. Not always that easy because the ecosystem is still evolving as well. But nevertheless, and on the other side, you have, a very complex scenario, and I'm sure many of you deal with it also on a daily basis, is starting everything from scratch. So that can be a bit challenging. You have new teams, older team guys have left, the new guys have come. There's a different code base. There's no lack of there's lack of proper tooling and processes, and so the reality eventually becomes how to sort of hand over a model from another team, do re-implementation, adapting into production, and if you have a serious gatekeepers in these environments, you will definitely never have these models accepted in production. Production is serious business. There are hundreds of millions of dollars, depending on, even in smaller companies, they've invested into their IT and their systems. The business is integrated. So I guess you do understand what that implication is. But it's very important to understand how these two, sort of both spectrums work, right? So on one side, you have homogeneous and seamless, so things are working, but there's a lot of investment that went into these companies, and they spent years actually to evaluate, down select, and eventually work with proper partners. And on the other side, you have your scratch, building out from scratch and sort of distributor model. You train somewhere else, you deploy somewhere else. Your customers are also, that'll increase a lot of hassles. You will never be able to streamline things. So just wanted to give you this example. So it becomes super crucial for you to perform validation in an environment that actually starts mimicking your production environment. That's what you need, and that's what we call an acceptance environment. We call it a validation environment, I guess, in a machine learning landscape. But we've been using this for almost a few decades. You have these sort of disciplines before you put models into production. So the lesser the hassle in your development and zero hassles in your acceptance, you have a great seamless strategy. And sure enough, I mean, not every company has a perfect homogeneous and a seamless sort of transportation mechanisms. So you always hang somewhere in the middle because you want to use take advantage of all the best tools and practices of your platform. And do keep asking questions. I see there are questions arising. I just switched my browser. So I'll keep asking. CI/CD obviously can be used. Yes, Arun. Let me go back to, so development production is one aspect, and then tooling consideration. So the next is tooling consideration, all right? So I took a more modern example. So, if we were talking about machine learning like 6, 7 years ago, you'd be looking at this. Let's see if I can point. Can I point my mouse? No, there's no way. Oh, I can annotate laser pointer. Yep. Yes, my laser pointer works. So basically here on the right here, you have your PMML. That was the predictive model markup language. Those kind of frameworks used to exist before deep learning came in and took the throne away from the ML sort of, um, So essentially, you have to have some kind of a tooling considerations. You need to have some kind of a format you need to send to production, and it should be considered already early on. Um, it should you should think about it as if it will have a large sort of impact on the model itself, and the quantity of work that you will need to actually take these into production, and have to think about it from uh, uh, sort of a very practical perspective. So I've just put an example of PyTorch Lightning just as an example because I see a lot of folks are using PyTorch Lightning right now and experimenting and putting these into development at least. So and for example, if you were to take a model which was developed in PyTorch Lightning, and then you essentially expect Onyx, which is the open network, which is what we use as well. So just took an example of a little bit more modern interoperable framework on the left here. So here on the left, and essentially you need to plan to ship the format early on. So that's very important. Whether you are still using older methodologies and your data streams consist of all of the kind of data sets that still consume and serve your business. So it really doesn't matter if ML or DL. It's not about fashionable stuff. It's about what works for you. Um, so depending on ONNX or PMML, which if you're using, it makes a lot of sense for you to understand how to sort of, plan ahead and plan the formats of my models ahead. So setting up tooling obviously makes a lot of sense as well. So you need to sort of plan to design even before you actually started considering building your model. And then you need to have robust validation. So essentially, your team should be able to, set up tooling while developing the production. There should be already a first version of the model finished, let's say, or even get started. And then, if you're not able to validate this, you will end up in having serious trouble into production. So your tooling consideration is super important when you're developing in a certain framework. Passing it through an interoperable framework, it makes a lot of sense. For example, Onyx is interoperable. As you can see here, you can push all kinds of models into Onyx, and you can load from Onyx. That's what we do as well. We call it a FARO. So ours is a fast API, React, and Onyx framework. And internally, we have code named our own sort of platform that we're building, faster than light. And the purpose is actually to very quickly and very efficiently ship models through a certain framework and eventually serve into various environments. So one customer would probably want, or one stream would want to consume it in an Azure environment. The other would want to consume it in Google Cloud, etc. So that's super important. So having proper tooling considerations is very important. So you need to plan ahead. You need to be able to set up your tooling in advance as if you were shipping a model tomorrow into production, even before you started developing a model. And then having a proper validation in place in order to make sure that your pipelines that you've created are going to be validated. And it shouldn't be performed on a PyTorch Lightning model, for example. That was not going to work. It's not the one that you're putting into production, right? You're actually taking it and you're essentially you're shipping your model into production. That's what you do. So if you start doing the other way around, you will run into serious trouble. All right, just keeping a track of time, 22 minutes. I said that it'll be not more than half an hour. So let's kind of take up the speed a little bit and go into performance consideration. That takes a little bit of a few minutes, not more than 2-3 minutes. So the key considerations out here are several, actually, but let's just focus on a couple. So we see that increasingly in our own projects as well. Quantization is one of the key things, has been discussed. There are a lot of theoretical articles out there. But you need to understand that the most important reason to be able to convert your models is for performance. That's what you do. You're either reducing the size, you're reducing the model size, you're distributing these through various pipelines, and makes a lot of sense for you to do that. So as an example, if you have your Python model that is typically has a high latency for scoring a single record, than to its equivalent that is converted to C++, for example. And the resulting model is likely to be, tens of times faster than the model that you would have ideally sort of, or not ideally, that the model you would essentially would be putting into production. So think in terms of, it'll have a high latency. So that is where you need to start understanding, okay, so why do we need to ship these into C++? Having all kinds of, C++ bindings, making sure that your application is running super fast. Performance also actually is very important when a production model needs to run at a low price devices. So today there's a lot of challenge around, have big and massive compute devices, and all you do is, crunch and train massive workloads. But eventually you have to put these on commodity devices because that revolution is one way or the other going to happen. You cannot have exponentially increasing GPU prices. And eventually you're not going to expect everybody to be buying these hundreds of thousands or maybe millions of dollars worth of servers in high compute environments. So essentially, no matter what the development in the infrastructure or technology GPU world is, you need to be able to serve your model, prepare it as if you were serving it to your customers on an app. So it has to be run on a low power device. And that's super important, especially when it comes to inferencing. And I would argue that even distributed computing should happen on commodity devices, but that's a different discussion. So for example, you train your model, they can become extremely large with billions, today, even trillions of parameters as we have seen in language models. And it's impossible for you to do anything, sensible, unless you're doing it through an open API, efficient APIs to serve it on simple devices, and having these and essentially allowing inferencing capabilities on standard machines and infrastructure ecosystems is going to be super challenging. So these models are not optimized enough for runtime. That is what we are trying to understand. And to have better performance, the model definitions, they have to be optimized. That's what performance is all about. So there are a bunch of compression techniques that you need to do that. So just a very quick sort of high level overview on quantization. So quantization basically, the model, it can be trained on a 32-bit floating point numbers, and it's used for inferencing at a lower precision, essentially, so that the model requires much less memory and it's much faster, actually, while the accuracy can be preserved, right? And it basically refers to the process. Quantization is a process of reducing the number of bits, essentially. So you're 32-bit, and you're able to reduce those to 16 or to 8 bits, and still have the performance of the floating point 32. So essentially, what happens is you reduce the memory bandwidth, and that's super important to do that. Pruning is where you simply are basically removing weights, and sometimes you can also eliminate complete network layers to depending on which situation. That can be super important and super exciting as well. And depending on the situation, you can sort of achieve some interesting results as well. And then you have it's still kind of a bit radical approach. So you need to sort of understand how to kind of do your pruning, but it tends to work in certain situations. And then you have distillation. So distillation is basically essentially it's almost like having a smaller student a network that is trained to mimic a much larger model. For example, today, there are a bunch of strategies that people are deploying to actually, mimic large GPT-3 and all these models to try to kind of use some sort of distillation techniques. And there's a lot of distillation activities and projects that'll be coming up, open source projects, on people trying to understand and make sense of these large models and how can I sort of train the small student network, learner network, as I call it, to essentially, mimic a much bigger model. So if it's, if you're able to do it properly, it can lead to really better models as compared to trying to train a smaller network directly from that data. That's not going to work. So these methods are efficient, and there are many other techniques, and I won't go into that. Weight sharing sort of is one such technique. Low rank optimization, binary, ternary net, etc. So these methods are super efficient if the initial model is trained in a way that reduces the information loss. That's what we're trying to solve, right? While performing these, and so the operations are not to simply convert the trained models post hoc, but rather, you're orienting the way the model is trained, and this is where actually it becomes very interesting. And this is very important in testing as well, because testing is not just about doing bug fixes, etc. It's all about trying to test more performance strategies, right? So that's why I kind of put it under an umbrella of testing strategies. All right. So it took a little bit of a time explaining this, but again, I mean, this high level, like I said, there's a lot of interesting literature available to understand. We also internally sort of train our own folks as well. Our researchers, senior researchers, keep sort of talking about these techniques and how to use these in niche and sort of novel projects. And that's very important to understand. Data access consideration is also very important. So this is the last sort of aspect of this performance considerations in your testing strategy. So model evaluation versus user input. So what does that mean? Basically, what you're saying is your model could expect something, but essentially, when you're launching your model into production for data access, it'll evaluate things like, let's say, the price of shoes, for example. Use the average market price for the shoe price, etc., or think of some other sort of maybe more understandable concept of, let's say, real estate or housing prices or something like that. So essentially, what you're asking, what you're putting in your model for evaluation techniques is not what the user or the system is going to request, right? So the scoring is not probably going to provide you in averages, and it will sort of likely lead to people searching on a zip code or looking. So you'll have to create some sort of a lookup sort of tables, and that's what I keep talking about in many sort of also practical and real world client conversations. Is not everything you're able to put and squeeze inside your model. So you could have your model, but you will not. You will have to create. I don't know if I can sketch here. Let's see. Pen. So essentially, what you could have here is, you could have your external database, and essentially, in here you have lookup tables. I'm just pushing it here. So essentially, you're just providing. So you're not providing on the fly from the model itself, but you're also sort of doing your lookup here. Lookup, it looks pretty ugly as I type. So this is what you can do as well in using databases. Is very efficient. I think all experienced machine learning guys know that they need to talk to their database guys as well if you want to achieve that. So let me go back to my laser pointer. All right. So essentially, database is super important. And then you have to plan for versatility and extensibility. So managing this setup and configuration is quite complex in practice, and it requires having more integration and having an integrated sort of model, and integrated testing becomes a challenge as well. So anyways, model validation in situations, when you're using external data, for example, then it becomes kind of, it has to closely match your production environment, and it becomes equally sort of essentially quite critical and technical from connectivity standpoint when you have to have a common source of production sort of challenge that you need to solve. So that's why it's super important to plan for versatility. But be careful that you need to have diverse skills inside your team in order to have this validation. That is not just purely an in-model exercise, but it requires external resources, external sources as well. So just to summarize, let's see how much time do we have? 33 minutes. So that still gives me time to go quickly into the testing strategies. So basically, focusing on inferencing optimization is super important. Training a model usually it requires sort of massive computation, a high level of sort of software sophistication, big data volumes, and massive machines and powerful GPUs, and we all understand that. But actually, the whole life cycle of a model, there's a pretty good chance that most of the computing is spent, and as you know, if you have online systems, most of the work is actually spent in inferencing. It's basically keep trying to understand and learn from the model and keep improving it. And this is where MLOps becomes a moving target, as I mentioned. Lowering the complexity. So basically, you scale for speed, but you have to optimize for your environment, and also optimize for that. Am I sort of burning too much GPUs, and it affects the ecological sort of footprint of how we work, versus how do we sort of optimize these. So you have to lower the complexity of models. You have to compress these extremely complex models and essentially lower the operating costs. And this is how you can also reduce your technical debt, which people have also spoken about. It is going to become a huge problem if companies are not able to comply to, well, we are sort of our computation is 60% green or 70% green based on this is how we efficiently run things on low power devices, on not high end sort of storage, networking, compute power. And those all will affect your ecological footprint. So that's very important as well. I mean, I know it sounds very exotic if you're an engineer, some guy talking about the green flag, but I think it's very important to consider this by design, very important. There's no need to keep pushing so big, huge UNet models to fit a problem. Sometimes you don't even actually need machine learning, to be very honest. Not every problem has to be solved with machine learning. You don't need ML. You can still use simple lookup tables, searches, etc. in your databases, which are super efficient already for decades, 40 years already. So those are the kind of techniques you should keep using as well. Not everything needs to become a model. Not every sort of 10,000s, hundreds of thousands of rows in an Excel sheet or an SQL databases needs to be converted into some kind of a trained model. So think about that, and it's very important to sort of see that there's complex stuff in experimentation, but push stupidly simple models into production. It's really important to practice to control the complexity of a model, is to develop complex models. That's super important. They can achieve the baseline. They have top performance. If you're a competing company, especially if you're a startup, it really is important for you to actually break the bank. But when you start taking these into production to your end user customers, it should be simple as simple as anything. And this is where actually it makes a lot of sense. And so this is how you take advantage of sort of you reduce the operating risk of your model. You increase the computational performance. You're lowering the price of consumption and the power of consumption, and essentially. A simpler model actually meets the production and is a star inside production. So that's something you need to sort of also pay attention to. Let's see, I'll spend another 10 minutes in testing strategies. However, I realize it's a long topic as well. So perhaps I'll just, so testing is super important. I just want to kind of get a heads up and see how many of you folks are still available online. Let me see, and if it still is interesting for you guys. So just raise your hand if you want me to continue on our testing strategies. If this was already enough for you to consume, we could also resume this into a third session. So are you guys, do you guys want me to continue? So we'll spend another 10, 15 minutes. I won't take too long. Is that okay? A few guys, if you raise your hand, I'll continue. Let's see. So I guess I didn't hear a yes. I'll continue. No, never mind. Awesome. So testing strategies is essentially testing. Well, testing leads to flaws. I picked up a quote on brainyquotes.com. But solving flaws actually leads to better understanding, and that is a common principle which we forget. So model testing, it consists of applying the models that are carefully curate the data and validate the measurements against the requirements. That's what we're trying to do. What we want the model to do when it touches and hits the production, does it do what it should do? So how you select the data, how you generate, as well as how much data that is required is super crucial, super important. But it's also dependent on the problem that is tackled by the model. All right. So what are these aspects that we're looking at? So there are also situations in real world situations when your test data does not match the real when you're testing it does not match the real world data, and this is problematic. So scenarios in which, for example, let's say you could prepare a bunch of scenarios, and some of them should match realistic scenarios as well. And other data, they should be actually generated in a specific way in order to be able to match to the model that you have developed. And if you have things like extreme values or missing values, if it's tabular data, or in visual, I guess in computer vision, things should be curated, especially when you're moving a specific, let's say in healthcare or some other sort of project. You will curate it. You will obviously make sure that not random data is coming, but people have tested it with various different types of data, and then suddenly tends to kind of confuse the model. But again, it's important that your test data should match the real world data. It doesn't happen always. Second is there has to be some sort of expectation, sort of a balance. So you have your statistics versus computation expectations. And then, for example, the things like metrics that you use in statistics, what are these metrics, right? So they are accuracy, precision, recall, etc. And then you have your computational sort of expectations, like your latency, your latency percentile, 95th latency percentile, etc. And these aspects of the test scenario, they should be able, these are the sort of test expectations that should be met. If not, then the assumptions that we make are not verified, and therefore the test should fail. That's the testing strategy in very simple terms. So for example, your testing strategy could be if the model does not have an accuracy above 90%, it fails, right? Or if your inferencing time is more than 50 milliseconds, it fails. Or if it's takes 5% of the inferences even you can also carve these out. So if you say like 5 or 10% of the inferences take, I don't know, 100 milliseconds, it should fail. So basically, you're already trying to provide very strict sort of expectations. And these assumptions in software developers, if you are one, you will know you tend to have these expectations, and you call these checks, or you put these asserts sort of commands. So these are the assertions that you use, and that's what you do in traditional software development. So statistical tests, finally, so that's sort of, it's important. So how assertive are your assumptions, and make assertions and sort of have some kind of like threshold to be able to test these. And increasingly, as I said, designing your model from explainability and ethics, privacy standpoint should be the thing you should be doing already from the beginning. It's very important. It's not anymore a nice to have exercise. You need to do this if you want to take these models into production that will be audited. There's going to be a governance board. And if you don't have these models that can be auditable, then probably it would be very risky for you to take this model into production, because you could run into large fines, as you know, that in European Union and probably other countries as well, there will be checks and measures to do that. Anyway, so statistical tests actually should be performed, and things like, very simple example, fairness testing, for example. So you can do statistical tests, and for example, in subpopulations, it's very important to know that you can compare the model with the previous version, and it allows you to actually put in place some sort of an approach. I think I read in one of the a wonderful book that the guys wrote from Data IQ. They called it a champion and a challenger approach. So you need to be able to check that a metric does not suddenly drop, right? So if you're for instance, it can be pretty useful in designing test scenarios by splitting the data into subpopulations based on the sensitivity variable. So what is a sensitivity variable? In this case, could be gender, or it could be any other sort of aspect that can lead to some sort of a issue in your fairness check, a fairness test. And sort of, that if you have a sensitivity variable, which may or may not be used as a feature in the model, but this is how fairness, typically, for instance, between genders, like I said, or other ethnicities or other aspects that are sensitive, can be evaluated. And all models actually that apply to people should be analyzed into fairness. So this is how you should actually look into each and every model. I know it's frustrating. I mean, 5 years ago, we never thought we'd be doing this, but it's super important. So if you're not able to assess the model's fairness, you will have business, regulatory, and reputational implications to your organizations. Many companies, large internet companies, are already facing these challenges. Again, this is a simple example I picked up on the internet. I mean, this just shows basically simple sort of test of how you are able to have a simple example project. So in this case, I'm defining, for example, cube or cube root, or not cube root, just cube of a certain number. And then you have your document string to explain what you're doing. It accepts a list of numbers and returns a list of those numbers cubed. And then essentially you're just doing a simple, and this is just a very basic example, test sort of, codes and the utilities is what software and machine learning developers should package and pass these utilities into your pipeline. So essentially, it's very simple. You write a test for functionality, and then write the functional code, and then essentially you refactor the code to make sure that it fits the structure. So that's what you do. So in this case, what happens is, before you're implementing, you're assuming that your function is written correctly. You do exception capturing. It throws an error, or developers call it exceptions. If the numbers argument is not a list, and then you have a standard response. If the list is returned, the number at the index of j is returned, is equal to the cube. It should be square cube of the number at the index of j and the number's argument, etc. So it's a very simple, basic example. So basically what you're doing is, after specifying and writing the test cases, you can implement the cube underscore list function. Once that function passes all the tests, you can be pretty much confident that your code actually achieves the desired functionality. So this is just a sort of very basic, simple example of what full-scale testing should look like. So it's very important to have your test strategies understood well. The massive benefit of test sort of driven development is the techniques. It produces well-tested code rather than just code, which I don't know if today, if someone were to do some kind of a benchmark, you might probably see that there's a lot of chaos already happening out there. So I think I spoke about this last time a little bit. I can again revisit these. So this is how the whole testing paradigm looks like. So once again, I mean, it's not a sort of a 4-hour lecture on testing. So for that, there are different courses. And we have our own courses to do that. But just to give you a bit of an idea, you have your experimentation tests, so the green, the purples, the browns, and then I guess the greens again are essentially the paradigms of experimentation, data operations, model operations, and DevOps, essentially. So basically your UI, UX pipeline. And then there's things like I mentioned last again. So for example, a simple example of differential testing, it's kind of a type of a test that compares differences in execution from one system version to the next, and essentially when the inputs are the same. So it's also called back-to-back testing, and it's pretty useful in detecting your machine learning or deep learning system errors that do not raise exceptions. So that's very important to understand. And tuning these sort of is a balancing act, because the more you have these testing, obviously slows down your system. So you have to make sure that, but they definitely need to be in your production environment. And the most important thing is it saves you from extremely painful problems when you have in production. So that is why I think, so it's just again a bit of high level on testing paradigm. And then I go a little bit deep. Let's see how much time we 48 minutes. I'll spend another, I guess, let's see how many of you guys are still online. Just wanted to kind of make sure that I am serving you and helping you guys understand. Awesome. So I still see quite a number of people are still online. So apparently you seem to be enjoying this. I'm grateful again. Thank you for this, honestly. Awesome. So basically, testing machine learning models is super important. And I suggest going a bit sort of uh, deep dive. Just like sort of software, you need to be able to have your machine learning, like I said, they should be validated before testing. So essentially, during a production planning, you have your holdout performance testing. How do you do that? You validate the model's predictive performance on a holdout set or a held out set, and essentially compare it to a predetermined minimum accepted threshold. So the metrics and the threshold combination defines the minimum level of performance a model should achieve before it can be deployed into production. Second, test for different examples. So computing a model's performance against a held out data set doesn't always tell you everything, right? So basically, sometimes there could be samples of data where you want always a model to produce a specific outcome. And essentially, finally, the testing on subpopulations. So this is where we start looking at when you start reducing the information contained in the predictions down to sort of a single sort of metric, such as an accuracy. It can produce some, these aggregations can produce misleading results, and that's where you should be very careful about. So basically, a model performance on a specific slice of data can be very different than how it performs on an entire data set. So that's how you need to sort of start understanding of the things like model fairness, et cetera, and how do I sort of test these on subpopulations. So be careful about that. So, and then there's this ABC testing. I have the sources already sort of provided sources, so I picked up some interesting ideas, and essentially it's the same thing. I mean, on the top, I'm talking about how ABC testing works. So there's a difference between, so until now, we were just talking about offline testing, meaning we're doing everything. We have the data set, we do everything. There's nothing going on online, and you're just serving and producing a model, and it's serving your business. When you move into the online testing, things change quite radically. So RCT is pretty sort of well-known a technique. It's called random controlled trial. If you do medicinal tests and et cetera, and COVID, for example, there's a lot of RCT that may have happened in COVID testing before the vaccines were generated. So it's probably a great example actually of doing that. I don't know if they used also machine learning, et cetera. I'm sure they must have. Obviously today it's embedded elsewhere, all over the place. So essentially, the offline sort of tests are used to validate data, as we just mentioned, and we went through. It validates infrastructures, validates models before deploying these into production. So they can be used to demonstrate actually adequate model performance on historical data. And these tests cannot be, they cannot establish the causal relationship between a model and the user outcomes. So when a machine learning is introduced to drive specific user behavior, for example, like a click-through rate, you have your online product, you're constantly trying to be in front of the customer and trying to give him the best or her the best deal for your product. This is where you need to start doing online validation or experimentation. So basically, a simple A/B test or RCT is a sort of a well-known sort of product development process, mainstay sort of process, and can be sort of thoughtfully explored through all kinds of examples of developing, like I said, medicine, developing a product, testing a product against your consumers. And why do we do sort of online experimentation? So online experiments are usually sort of they're used to measure the impact of action against some baseline according to a specific metric. So, for example, in a UI example, the control is of the original at the bottom, for example. So you have your red, the control, and then you have a new color green is the treatment. And the metric that you need to measure is the click-through rate of that button. And in order to establish the causality, you need to perform this in a controlled randomized experiment, right? So one experiment, it's known as, like I said, the AB. So you have two distinct or non-overlapping cohorts, and one cohort period of a time you establish before the experiment begins, and then you measure the click-through rates from both the cohorts. And if the metrics is higher, then for, let's say, the treatment or whatever your consumer, if you're a consumer company, then you conclude that the new color causes the increase in the click-through rate. And that's how you actually make the conclusion. And you say, okay, so we're going to go with B. And then you start actually also pursuing various archetypes with various strategies. So A, B, C sort of testing experimentation techniques. So you can roll out potentially the green button either to all your consumers or to a certain set of consumers that act on a certain sort of behavior. So this click-through rate actually drives you. And essentially what you see is that if the control has a higher click-through rate, the green button doesn't cause the increased click-through. And therefore you keep the original red button. So it's a trade-off. Cool. So I hope this was a bit clear, and it's can't explain everything in this ABC testing. There's many sort of interesting sort of literature available online. This is the last sort of slide, and then we'll conclude the performance and testing sort of strategies, or performance actually under the testing strategies. So in a real world example of a machine learning A/B test, and there are ways to do that, and I won't go into detail in how do you actually do this and how do you deploy this in a cloud environment like Amazon or in Google Cloud. But for now, let's just focus on this example, which I picked up also on SlideShare. I have a link provided. This was a very nice example in which this guy had explained. So I just want to kind of sort of take this, and I resketched this diagram, by the way. So essentially what you see is the offline tests and the online tests. You see the difference as how the workflow looks like. So essentially you have to validate your hypothesis. That's your endpoint. And you're constantly doing your offline hypothesis validation. And when you have done it, then you design your A, B, C tests, depending on how your archetypes are sliced and who you want to serve. And then you pick your control. I just took the example of that in the previous slide. Deploy a prototype, observe the behavior, check the results, and then if you have any improvements, any significant improvements, yes, boom, you deploy the feature to production. No, then it goes back into the hypothesis, the original hypothesis in your offline tests, and you do the same cycle. And this workflow is super important when you're doing sort of A/B testing. So when you roll out new models to your client base, it does mean that you need to have additional validation set or additional validation step, actually, I should say, before rolling out or deploying features to all users. And finally, there's another problem. So there was a very interesting research done by these guys from Booking.com, and they concluded, because Booking.com, Netflix, think of all these companies that constantly, Booking.com, unfortunately, it's an unfortunate example in this COVID, because people not flying, it's very difficult to understand where does Terry want to go from A to B, where does he want to stay? So all those beautiful things they were doing. So they wrote a beautiful paper. It's not, unfortunately, not available. The title is 150 Tests or something. It was very popular a few years ago, but very interesting conclusions that the team were able to make. Booking.com is a Dutch company. And essentially, sort of what they concluded was that there are many things that happen, and you cannot indefinitely keep increasing the model performance and assume that it serves your business and provides you business value. And what do I mean by that? So basically, you can do a lot of sort of online tests. You can roll out new models to the user base, and essentially. But the thing is, the concept of how you correlate your offline metrics with A/B tests is still not a very well and easily understood feature. And this is what the booking.com researchers tried to sort of provide the insight. And they said that, you cannot keep, like I said, keep increasing because it doesn't help. There are things like value performance saturation. So what does that mean? It's not possible to keep sort of continuing to deliver deriving business value from models improving indefinitely. It saturates, it plateaus at a certain point. There is segment saturation as well, or the segment that you're serving, right? The archetypes, and then you make your own segment to serve these specific customers within these segments. And over time, the treatment groups sort of the decrease, so it becomes very difficult to statistically get significant gains in value from those segments. And then there's uncanny valley effect, in which certain users are unsettled in how well models predict their actions as model performance improves over time. The negative effects affects the user experience. And then finally, then you have your proxy over optimization, where models over optimize the observable variables that are proxies to certain business objectives, because that is not something which the business wants to solve. It could just be sort of a distraction. And this is not what you want. You don't want your model to have 99% accuracy is not serving your business. So basically, it has to be aligned to these variables that may have high accuracy metrics, great precision, great recall, but if they do not serve actually a business value, what I mean by that is that your business objective was to do something, and then it's not doing that, and saying that your model is doing great is not the way to go. Awesome. So I think we spent 1 hour exactly, and I'll take questions. So testing. So basically, you have to test for better business outcomes. It's not just about tech. So no matter how fascinated and excited we are about AI and machine learning, it's very important to understand that your validation procedures, you should implement your projects. It depends on the complexity of the applications, and you need to make sure that your models are driving automated actions, and these automated actions are essentially serving business value, right? So that's very important. Testing offline and online, and they're quite different. We kind of understood it. So offline tests are sort of used to validate your model on historical data. You access the actual ground truth labels, right? But they're not the only type of validation you should perform. Online, in contrast, are necessary to establish causal relationships between a model and some desired effect, right? That's what you're doing. You're sort of experimenting this in the wild open space. And then you're essentially trying to chase a moving target, zeroing in, centering on that moving target, creating the segment if you don't already have, serve that segment to the optimal level value. Don't overshoot it. Don't try to start creating extra sort of frills and thrills, and then find that balanced approach to do that. And then finally, sort of online tests, there's one consideration, obviously, that when you do online testing, obviously your estate, the cost, and also the infrastructure, et cetera, the pipeline integration becomes a bit complex. So do make sure that you are having your teams in place who understand that as well. You cannot start actually expanding your estate. When I say estate, then I mean ML estate, the MLOPs ecosystem inside your company, unless you know what are the challenges, what are the extra effort and work required from us when we start using online testing as well, right? And consider sort of multiple design and test patterns for implementing A/B testing. And there are, like, I think in our MLOps training that we are developing, I've identified 50 to 60 design or test patterns, and we'll go through these in details, but that'll be released in the next few weeks. So I guess and there is in probably in the next lecture we'll talk about one pattern. We'll pick one pattern, we'll create a sort of a model, and then we'll deploy it, we'll test it and deploy it in an Amazon cloud or something like that. But I'll stop here, because otherwise we'll continue sort of to keep moving in that direction. And this is the course that I have. I'll just keep this open, so and I'll try to go and answer your questions. Let's see. I have two consoles. All right, so I see a few questions here. Let me just, in certain scenarios, Kaustubh has a question. In certain scenarios, data sensitivity is important to consider, and these off-the-shelf systems can be much more expensive from on-premise installations. Hmm, how do you navigate a situation like that? Uh, yeah, it depends actually, Costo, because I think we have also seen the opposite scenario where off-the-shelf systems, they could or could not sell sensitivity unless we understand, quantify, and have been able to identify the sensitivity of the labels and how deeper it goes into understanding and creating the fairness sort of flag as to, well, from the test assertion, we say 80% the fairness flag is green. Go ahead. I think it becomes it depends. Sometimes it's easier and inexpensive to actually build your own sort of testing strategy, especially on data sensitivity, on label sensitivity, what you're trying to solve when it comes to, especially around data from people. I think it's inexpensive. It's inexpensive sometimes to build if you have the knowledge in house. If you don't have the knowledge in house, then it becomes an expensive strategy because you're buying something off the shelf, which may also not be able to satisfy the need of your business unless you do the customization. So basically, you buy a product which is off the shelf, and I'm sure there are a few vendors who will be trying to say that. But then the customization probably will cost you maybe twice or thrice more because it has to adapt to what fairness means to you. Let's say within for your business, if you're let's say an institution, if you are a public institution, it's a very big thing. But if you don't have the budget, then it becomes a problem. I would suggest, how do you navigate a situation like that? I would suggest is to train and hire people, bring people from interdisciplinary domains, social science, also political science, historians who understand the context can very quickly help you design that test pattern. And then basically based on that test pattern, that is the data sensitivity label, you can test it. And that probably is far more inexpensive to hire someone, pay $60,000, let's say if you're in US or in Europe, also similar sort of salary for one person, experienced person, train them in-house. That is the best way to actually mitigate that, I would say. That would be my strategy. Okay, you mean that if the data is restricted. Okay. Yeah. Okay, I understand. Yes, and yes, the cost obviously has a huge impact in each project, and I find it very frustrating because we also want to do some amazing projects with customers. So yes, I understand. In case of the data is restricted, that becomes quite a challenge. So I think there we are talking about encryption. That adds a layer of complexity. There's not much. There's some work going on. Some large companies like Palantir do that on a regular basis. I'm hoping because they do deal with a lot of defense data sets. Very very sensitive data around national security, etc. I think using and here, of course, the design pattern will be your encryption in how you're encrypting the data set, not just anonymizing, encrypted model training, encrypted model serving. And I think in select environments, I'm assuming that's why I mentioned Palantir, because that's the company that does that at a scale. But I'm sure that I know there are some defense contractors in US, not aware of any in the Netherlands. I'm sure there are here as well in Europe, for sure. They should be at least, who have a decent pipeline to actually deal with the data sensitivity. Cool. I do not see any more questions. I am going to see if there is something going on LinkedIn. If not, I guess we're good to go. So I guess we're gonna put this to a stop. For some reason, I'm not able to look into my own live. Nope. So let me just see. And then if not, I will thank you all for all your wonderful questions. And I really appreciate it that you were able to stay here and talk to and sort of share with me your experiences and also your questions. So if you have any questions, do keep please asking these questions here. Um, I believe I'm still live, and yeah, somehow I cannot see this anymore. My LinkedIn is cool. So thank you. Thanks, everybody. I really appreciate it. If there are any questions, drop me a note, and I am going to super sort of definitely respond to your questions for whatever that I can. I don't have answers to all, but I will do my best to answer. I really appreciate you hanging along and staying for an hour with me. There will be more interesting MLOps perspectives. We will be adding model registry, how to do DevOps within the model ops and how that is changing with low code and no code. So there's going to be a lot of fun stuff coming. It's all high level, I know. You have to go into the depths to understand it if you want to really run these and understand the full ML ops ecosystem. So if there are no more questions, I'm super grateful and thankful to you guys. And then I am going to, I guess I got disconnected. But anyways, so I disconnected my laptop. So thanks again, and I hope to see you guys soon in the next call. Take care. Bye bye.